This video is going to introduce the idea of kinetic energy and work a few simple examples that will show us how we can use the form for kinetic energy to relate back to the work and energy theorem. Let's imagine we have this car and we apply a force. Here in this diagram it shows that we're pulling it on a string, but we have an initial velocity of the car and we're pulling it over a distance d. We know we're doing work on it, force multiplied by distance. We can expect that the final velocity of the car is bigger because we've applied a net force on that car, so the car has accelerated. So from that idea that we know that we're going to observe an acceleration and we're going to say that we did work on it in order to accelerate the car, we can actually get the form of kinetic energy, the functional form of kinetic energy. Here's how we're going to do that. We're going to say, okay, I know that my car is accelerating, so I can say one true statement is Vf squared equals Vi squared plus 2 times my acceleration times my distance, delta x, that I move through. Now Newton's second law allows me to rewrite this. I'll write the first part the same. Vf squared, Vi squared plus 2 times the force divided by the mass times delta x. This means that I can express my work, right? Force times delta x, force times distance, in terms of my changes in velocities. So I could then say that Vf squared minus Vi squared, that's moving this over, and then divided by 2 over m, that's going to equal F delta x. So I've just taken this equation and simplified it to solve for force times distance. Now why did I do that? Again, remember, in this diagram I know that I am accelerating and I have done work on the car because I've applied a force over a distance. So let's put those ideas together. We say, okay, my work has got to equal my total change in energy, but that's also equal to force times delta x by the definition of work, which means from that previous page, I can say that my work is equal to Vf squared minus Vi squared over 2 divided by m. Another way to write this is that I've got 1/2 times the mass, Vf squared minus Vi squared. All I've done is sort of made this fraction look a lot nicer by keeping the 2 on the bottom and realizing that mass, when I divide by mass on the bottom, I'm actually putting it on the top. I can separate this into 2 terms, right? I can separate this into saying I have 1/2 mass times Vf squared. Let's make that look a little bit neater. Vf squared minus 1/2 mass Vi squared. Now my work was equal to my, now I'm going to kind of fill this in down here, work was also equal to my change in energy. And if all that's happening is my car is moving faster, we call that energy of motion kinetic energy. So that work is equal to my change in kinetic energy. What we'll either call sometimes just K, sometimes KE, you'll see it both ways. And anytime I have a change in something, right, I can write that as K final minus K initial has got to equal, and I'll just copy down the top, 1/2 mVf squared minus 1/2 mVi squared. So that actually tells me that kinetic energy is equal to, so K final is equal to 1/2 mVf squared. K initial is equal to 1/2 mVi squared. So that tells me my overall general form for kinetic energy. My kinetic energy is equal to 1/2 mass times velocity squared. So I can look at an object moving with a speed v that has a mass m, and I can tell you the kinetic energy of that object using this straightforward calculation. So kinetic energy is our energy of motion. This car in this problem is moving faster and faster, and by this analysis sort of relating the work and energy theorem to our kinematic idea gives us that expression for kinetic energy. Let's see how we can use that by revisiting the problem of the gentleman pulling their suitcase in the airport. We knew from before that we had a work that was done. Given the data from before, we know that the work that we did the work was 866 joules. If you look back either in the previous video or maybe you wrote it down when we were solving the problem, right? We pulled with a force of 25 newtons over a distance of 40 meters at an angle of 30 degrees. So our problem now is we want to know how fast the final speed of the bag. Well, I know that the work has got to equal the change in energy of my system, which is going to be, for just a single particle system, which is my bag, this is my system, I can only have kinetic energy, so I'll write K final minus K initial. Again, you might see KE final minus KE initial. I frankly just am never careful enough to be consistent, so get used to seeing it both ways. K final minus K initial. Now, if we started at rest, our K initial is 0 because we have 0 meters per second as our initial velocity. So that means that the work that I did, 866 joules, is now showing itself only as my final kinetic energy, 1/2 mvf squared. So I can solve for my final velocity by multiplying by 2 and dividing by the mass. That's why in this problem I needed to know the mass of the bag. And I get a final speed of 21.3 meters per second, which is some highway type speed. Certainly much too fast in reality. The problem here is that we haven't talked about friction yet. So we're allowing this person to keep going faster and faster and faster and faster and faster and faster and faster. This is one of those frictionless examples, and over 40 meters we probably would have reached a constant velocity early on and maintained that constant velocity. So we didn't factor that in here. We know that the work done by friction, if we wish to just at least consider it symbolically, the work done by friction would be force times distance times cosine of 180 degrees, right? Because if we move this way, we know our frictional force on our free body diagram is always backwards, right? Against so I'd have 180 degrees of an angle between the two. That's going to give me a negative work done by friction, which would subtract from this total work done and thereby reducing my overall final speed. One last quick example. I know the video is getting a little long, but you don't need to watch it. You can do whatever the hell you want to do. Here we've got that car from that first example. Whoops. And we're going to think about how much work we need to accelerate it a certain amount. So again, we go back to our formula for work is equal to the change in energy. And here we've only talked about the change in kinetic energy. So that means the work that we do, which is what we're looking for, has got to equal K final minus K initial. So it's going to be 1/2 mass V final squared minus 1/2 mass V initial squared, just putting in our definition. Simplifying that, or rather I should say factoring out the mass, I've got 1/2 times 1,000 kilograms. And then my final speed was 30 meters per second squared minus 20 meters per second squared. That gives me a work that I would need of 250,000 joules. So while that change in speed isn't that significant, just 10 meters per second, we get a rather large work. If you dig into how the unit of a joule is defined, you see that a joule is actually quite a small unit of energy. It takes about 4 joules of energy to change the temperature of 1 cubic centimeter of water, which is like this, by this, by this, those little blocks you had in grade school. By 1 degree, it's not a lot of energy. So I need a significant amount of joules in order to change my speed by any appreciable amount. Now notice here, I didn't ask about the time or the distance that it took to move this car. The nice thing about energy, I only care about my initial and my final points. I don't care about time. Also, I don't know if I had a big force over a small distance just with this data. I don't know if I had a large distance and a small force. Both of them would give me this change in speed depending on what I have available to me.